Hi, good evening, everyone. Thank you for joining us in today's webinar. My name is Neeraj, and I am a data scientist at Analytics Vidya. Analytics Vidya is the leading community of data scientists in India and across globe. Today, we are hosting a webinar on Introduction to TensorFlow with Intel Optimization presented by Mukesh Gangadhar. Mukesh Gangadhar is the staff lead APJ in the Intel Developer Relation Division. He is a staff architect for optimizing software application on x86 platform, especially on the cloud and artificial intelligence. He has around 18 years of industry experience and holds a degree in Bachelor's of Engineering in CS and Electronics. Thank you, Mukesh, for joining us. For the audience, if you have any questions during the session, please type them into the Q&A session. So before Mukesh starts, I have a question for the audience. Do you use TensorFlow for deep learning or machine learning? Let us know by casting your votes, and after we are done, we'll share the results with you people. That is a great response. Around 62% of people have said that they'll be using TensorFlow for deep learning purposes. Okay, so now I'll hand over the webinar to Mukesh. Mukesh, the stage is all yours.
Okay, so my name is Mukesh. I'm not sure if I think Kunal already did the introduction, but I'll just do a quick recap myself. I predominantly work in a division called as Developer Relations Division. Primary focus is more on software optimization of applications on Intel architecture. So that's my primary responsibility, and I am here today to talk about introduction to TensorFlow with a little bit of Intel optimizations. All right, let's get this show on the road. If you have any questions, please maybe share it as on the screen, and we'll try to right away, or if not, at a later point in time as well. So a whole bunch of legal disclaimers. Blah blah blah, and things like that, right? Okay, so this is the agenda. I'm going to talk about a little bit on TensorFlow. I'm going to talk about neural networks with TensorFlow. Basically, just give an introduction. Primarily, I'm going to talk about the optimizations and performance comparisons on how you extract good performance on Intel platforms, right? Hope the agenda is covers all the aspects that we would want to cover today. All right. Okay. For folks who have not have not used TensorFlow, the basic aspect of TensorFlow is very simple. It's a data flow paradigm. It follows a data flow paradigm for doing any at least mathematical computations. It's a very good model for doing parallelism, specifically whether it is within a single node or across multiple nodes. The data flow architecture amends itself very successfully for parallel programming. So TensorFlow has and pretty much almost all at least majorly deep learning frameworks in today's at least the most popular ones kind of follow this kind of a paradigm. Right, it has capabilities both for deep learning as well as machine learning as well. So at least when I talk about machine learning, I'm talking about statistical machine learning. So it does have capabilities for that, and many of the algorithms you can actually get some of them at least similar ones using at least similar to traditional one packages like skitlearn and things like that. So you will be able to get some equivalent ones out of that. But of course, the basic aspect of TensorFlow is the data flow architecture. The primary interface is Python. You end up programming in Python, but the predominantly underlying computational tasks have been essentially written in C++, right? So most of the convolutions, or if you're talking about RNNs, LSTMs, most of them essentially have been offloaded to close to the native architecture, but but at least from a productivity standpoint, the primary interface for developers is essentially in Python. Another useful feature that most deep learning frameworks exhibit today is its integration with the scientific libraries like NumPy. So they know that the predominant data structure is quite understandable by packages like NumPy as well. So I think the other capabilities I talked about is implemented in C++, CUDA for taking advantage of the GPUs as well. And at least the low-level APIs have been programmed in such a fashion that it's really flexible. The onus is essentially given to the developer or the programmer in this particular standpoint to develop or create their models in the fashion that they would want. So a lot of let's say flexibility is given in that. Not many people are comfortable in developing with this kind of interface. TensorFlow has adopted models, additional frameworks on top of it, high-level APIs, using things like estimator and Keras and things like that, which for simplification purposes. So I think I have a Q&A. Let's see if I can answer that. How can we as small developers use distributed learning with TensorFlow estimators? Let's see if I can answer it online. If not, we'll definitely come back on that. So the question is, the basic aspect of estimator is the fact it actually hides distributed training for you, right? So it hides all the complexity for distributed training. So you can even for developers who are really not that nuanced about understanding the low-level TensorFlow APIs, they can essentially do so. That's one aspect of taking advantage of the estimator API in general. Or there are other ways of doing that. I'm not sure if you're aware of this, but Uber released an open source package called as Horobot, which also allows you to do distributed programming using message passing interface known as MPI. So the goal of Horobot was to do much better distributed training compared to what was default supported by TensorFlow itself. What about TensorFlow using R? With R, I'm not so sure. I think there are a couple of packages that are available which you can use R with TensorFlow, but I don't think it's not part of the TensorFlow environment. Predominantly, most people end up programming with Python. There is some support for Java as well, but at least as far as I know, I have not played with R. But I'm sorry about that. I don't know if R is a supported front end for TensorFlow. That's something that's available. Let's go to the next question. Let's go to the next slide out here. Okay, this is kind of a dated slide. This gives us a feeling in which TensorFlow has been slowly evolving. In fact, this is actually one of the most popular frameworks today. I think along with MXNet and PyTorch, and of course there are a whole bunch of other ones as well, like Paddle, Chainer, and a bunch of others. But at least what we see in the world today is TensorFlow is one of the most popular frameworks out there. It's a successor of one of the other frameworks that was internally built by Google itself. It's called as Distbelief. They open sourced it. They introduced a whole bunch of nice capabilities, right? So one of the things was to do inferencing, right? So if for people who understand deep learning, there's a training part, there's an inference part of it. So they essentially talked about TensorFlow serving as one very way of how you can do inferencing. Distributed runtime support came in because this was one of the most impressive features when Google actually released their paper. They definitely talked about distributed runtime as a key feature in the overall framework itself. But the first version did not have it, but the second version did support this particular capability. Interestingly, the XLA was an experimental feature, but right now I think it's still experimental. I don't think they do contribute a lot into XLA. The idea behind XLA is very simple. Since any deep learning framework is targeted on multiple hardware platforms, so the goal behind XLA was to see if they can take in the TensorFlow model and probably take all the computational operations and accelerate it in a fashion that when you're actually running it, if they can at runtime identify what is the underlying hardware, then they can probably create a more optimized model for that specific hardware, whether it is on the CPUs, on the GPUs, or probably on the TPUs as well. So that was the effort, but they're essentially doing a lot of activity on this particular standpoint, and there's a whole bunch of parallel effort that is also going on across multiple places to see how you can achieve a very similar aspect of having one common framework but targeting multiple platforms as well. TensorFlow Fold was a very interesting aspect of it. So typically, if you look at TensorFlow, you have to build the model from grounds up. So it's essentially it's what is called a static. So did not, at least the way most of the ones that we are aware of use a static model for either for training or inference. And TensorFlow Fold was supporting for dynamic batching as well. So so it's especially for variable input lengths like such as NLPs and things like that. So you did have support for TensorFlow as well. The current version is not 1.8. It's actually, I think, 1.11 RC2, if I'm not wrong, that is there. Okay, I think there is screen is stuck. I'm on slide TensorFlow history, so I think there is one saying that the screen is stuck. I'm not sure about that, so maybe. How do I implement or deploy your TensorFlow model in real life? Uh, okay, so addressing that particular aspect is going to be very when you say implement, I'm assuming the fact that you are actually creating a TensorFlow model from grounds up, right? If you're actually creating a TensorFlow model from grounds up, you would have to probably let's say figure out what's the use case that you're looking at, and probably have build a TensorFlow model from scratch for doing that. Or there are many popular deep learning community has is many of the researchers have apart from just releasing public papers, they also have released fully functional models. Now, depending upon what your use case is, and if you can actually take the models and then probably fine tune it for your requirement, that's probably one way to go forward. If you want to deploy your TensorFlow model, which is probably a case where you already have a trained model, then you would want to deploy it. Now that's a different issue altogether. That really depends on how are you looking at inferencing at the edge or inferencing at the cloud, or inferencing on the mobile phones. Depending on where you are exactly doing, you're actually going to run your trained model. So that essentially looks you're thinking about deployment stage itself. So it's a implementation to me would be implementing a model from scratch so that you can actually get a trained model and then go ahead and deploy it for inference. And I hope, Tarun, I think I kind of answered your question on that particular standpoint. Right. Let's go to the next slide. These are the popular, as I think I've already highlighted this, popular DL frameworks on the CPUs. So popular, of course, I talked about TensorFlow. Caffe is still being used, even though it was one of the very first deep learning models that actually came out there, but still at least many customers that I know actually use Caffe. So it still is a popular one to get started off. MXNet, started off from MIT, then I think Amazon kind of on MXNet as well. So for those folks who like Spark, you already have a Spark deployment or you have a Spark installation and want to add deep learning to it. So there is a very interesting project called as BigDL. So I would suggest folks to look at www.bigdl.org. It's a kind of an open source project from Intel, which kind of brings in direct support for deep learning within the Spark environment itself. So the interesting aspect is you can actually import your TensorFlow models, trained models directly into BigDL and Spark environment, and then probably run it as well. So it's got a whole bunch of features. So for folks who are more interested in playing around with the Spark environment, then probably BigDL is a way to go forward. Then of course we do support additional ones like FA2, PyTorch, CNTK, Paddle, and things like that. So the other ones are, there is this another open source project from Intel called as Intel Ngraph library. I would suggest people to take a look at it. This is kind of a graph-based compiler. So it's not a graph, it's not a graph-based compiler. Let me correct myself. It's a graph compiler. So it essentially brings in a whole bunch of optimizations for, specifically for data flow architectures, and also helps you target the specific hardware platform, in a very different manner. So we are, it's a project. There are, we already have introduced support for, if I'm not wrong, for TensorFlow and Cafe. So there are a couple of, let's say, as we call, bridges between these frameworks as well, so that both of them are integrated. And there's a very nice paper, a set of papers, at AI, this particular site called ai.intel.com. Please do visit that site. There are a couple of blogs, that also talk about how we actually build, graph compiler within TensorFlow, and the kind of performance that we're seeing at the end of the day. All right. Let's see if you have any. What version control tools will be used for DL models? That's a very good question. Right now, there are, the ecosystem for, all the surrounding tools for, this, let's say for deep learning models or your Python scripts or anything of that sort. It's essentially, it boils down to being a Python script, right? So your standard, let's say, Git or probably SVM or any of the tools is probably the easiest hack. There are some interesting, startups that are there in this particular space that kind of offer some of these capabilities, maybe at a later point in time. And I don't remember them off the top of my head, but you can definitely look that up on your more popular web browser, and I think you should be able to get access to some of them, right? But at least at least I do know that there are some startups who are trying to solve this particular problem. But right now, deep learning frameworks in general don't have any support for versioning or any of the other sort. So you are, you're free to implement your own version control. Will I get this PPT? I'm not sure. I think we should. We'll try to see how we can get you access to this particular PPT. Okay, I think can we make a executable out of TensorFlow model in Python? Yes. If yes, then can it utilize CUDA GPU power? Well, I don't think you can create executables of TensorFlow models, right? So because Python, you can create a let's say PYC, a compiled Python object, but I think beyond that, you cannot create an executable where you can essentially offload it. I think your question is probably more looking at since it's a text file, okay, how do I protect the model, or and things like that. But right now, exe support for TensorFlow models is not there. But I think there are other capabilities that are coming in. Probably you may, depending upon the kind of inferencing that you would want to do. Let's say, for example, if it is image or video processing, there's a tool from Intel called as OpenVINO. You can take a look at that. That does convert it into a more intermediate IR that you can essentially deploy at the end of the day. Or there's another way that you can probably experiment, which I have not tried out, but you can look at seeing if XLA can be of help for you. But yeah, you can take a look at that. But I haven't tried it out, so I don't know if you can do that. Yes, it can use, if it let's say, for example, yes, it can use CUDA GPU power if you have the CU-DNN libraries, and if you have told in the TensorFlow environment to take advantage of the GPUs, it will take advantage of it. So it really depends upon how you configure your TensorFlow environment at the end of the day. At the TensorFlow or the Python level, there are few static controls that you can essentially you can pass like saying that, okay, target device GPU 0 for running this particular graph. You can statically encode that within your model itself, or you can depend upon environment variables within the TensorFlow runtime itself for you to abstract your model out so that either it can run on the CPUs or GPUs or any other hardware. Depending upon which environment variable you choose, you can probably play around a little bit. I think one was Git, the other one is SVM. Standard versioning control tools. Whatever is out there, you can essentially take advantage of that. So it's almost like how you do source code version control. You can essentially do that as well. Is the performance numbers published on framework optimizations Intel? I could see. Yes, if I understand your question correctly, I think this is you're asking question of whether these are performance numbers that are published on Intel optimized framework for TensorFlow. Yes, they are. So the performance numbers that you see are from all the optimizations that we have incorporated. By the way, these optimizations have not stopped. We are continuously, working on these optimizations, and as we go along, we'll definitely improve them as well. But this is probably a good place to start, or if you want to, figure out where we stand and things like that. So you could see a whole bunch of public numbers out there. How does Neon perform on standard frameworks when compared to TensorFlow MKL? Well, okay. So Neon itself is a framework by itself, right? So, we have optimized Neon for for taking advantage of IA Intel architecture, but currently more considering the fact that TensorFlow is probably the most popular deep learning framework, our current effort is trying to make sure that TensorFlow has all optimizations for MKL. Not just MKL, but a whole bunch of other capabilities. I hope, hopefully, I think by the end of this presentation, I'll probably, quickly take you through that particular aspect as well. Okay. All right. So let's quick, go to the next one. Okay. So this probably I'll come back to this. The reason why we needed TensorFlow, optimizations on the CPU is by default, the computational operations on the CPU were quite slow, and most of our effort has been to ensure the fact that the underlying computational operations have been written in a fashion that they leverage the underlying architecture in a much suitable fashion. So that's so you will definitely see this continuous work from Intel, and the aspect is it has been upstreamed and it's ready to use. So all the optimizations that we're talking about is actually available on the master branch today, and you should be able to take advantage of all these optimizations itself. Okay, so for folks who have who do not know too much about TensorFlow, it's essentially based on three underlying let's say classes, but there are a whole bunch of other classes which I'm not going to cover in general, but at least for our purpose of today's talk, I think we'll focus on these three, right? So remember when I initially started this particular talk, I mentioned the fact that this is a data flow architecture. So the data flow architecture is essentially think of it like it's like a graph, right? So you have you have a vertex or a node, and you have edges that are either coming inside the node or either exiting from the node itself, right? So the operations that TensorFlow essentially defines as nodes in the particular graph, and they effectively indicate computation. So if you're doing let's say a matrix multiplication or probably a convolution, so that would be essentially defined as one node in this particular graph. And tensor is essentially the data. So a tensor is very simply a matrix. It could be a 4D tensor, it could be a 1D tensor, or think of it like a single dimensional array, 2-dimensional array, 3-dimensional array kind of a thing. So it's the terminology that that is very popularly used in the deep learning world is the concept of tensor itself, right? Numbers are slightly confusing. Okay, so the numbers in the previous slide are slightly confusing. Is 14x performance in inference, 3x performance in training. In general, is performance inference. Yes, inference is faster than training because I think I'll probably answer your question in a couple of slides down the road. So probably just wait for my answer. If I've not answered it, please ping on the Q&A, and I'll try to answer it as if as soon as possible. Okay. Right. So let's take a look at this particular graph. So this is kind of a pictorial representation of what I just talked about. So what you essentially see, these circles are essentially nodes. So they essentially define computation. So in one of the blue color ones is where I do a multiplication. The yellow ones are essentially the ones that I do. Orange ones are where I do an add, and the yellow ones are essentially ones that I ask for input. And you actually see the edges. So what essentially means to say that I have for the multiplication operator, then I have two inputs coming in. For the add operation, I have two inputs coming in. Multiplication has one output that essentially feeds into the second add, and so it's almost like a graph-like representation at the end of the day. Okay, so going to the next one. So these are the lines between the nodes refer to the edges, right? So this is how data flows. So the data flows from the input to let's say one of the to mul, and that's where one of the computation operation happens, and then it could flow into the output of mul, flows into add, and then essentially to the next stage of computation as well. So the data is essentially flowing from one node to another node. So that's the aspect that you would have to remember. That's very common in many of the data flow architectures. For a very simple example that you have, if I have two inputs, 7 and 3, which I give, in this particular case, since remember, mul essentially has two edges coming in, one from 7, another from 3. So I do a multiplication, which becomes 21, and then I feed it into the second add. The output of the second add is 10 because it's also got two inputs of 7 and 3. So it's a very easily representation of the kind of computation that you would essentially do, and and this becomes easily parallelizable because I can take multiplication, probably run it on one CPU core, take the second one add, run it on the second CPU core, and take the third add, run it on the third CPU core, assuming that I have good amount of computation within all these particular nodes. So it becomes very easy for me to pass on distribute data across either multiple computational cores, and then probably achieve parallelism in a very easy fashion. So a couple of at least let's say how you would take advantage of how do you define variables at the end of the day, right? There are multiple ways by doing so. One easy way is essentially to define a constant, right? In the earlier case, in the earlier example, if you take a look at it, we had defined as 7 and 3. So I would probably as TF constant and assign the value of 7. So throughout the the lifetime of this particular model, the constant value is not going to change, right? But that is really not what you would want. You ideally want to feed in dynamic input, because you're training or you're running your model on let's say different data sets at different points in time, so you don't want to have a constant. So TensorFlow has this very interesting aspect called as TensorFlow placeholders, right? So what indicating in this particular standpoint is you are essentially indicating to TensorFlow that, hey, I am creating a placeholder of type float 32, and I'm giving this name as input 1, right? So all you're essentially saying is I'm just creating an area, and I'm defining this as input 1, and it's of type float, float 32, right? And in this particular placeholder, I can feed in any data. Today it could be maybe right now it could be 7, maybe the next time it could be 3. So I can dynamically change the inputs, right? So placeholder is essentially gives you the way by which you can dynamically feed inputs into a model, and thereby bring in some sort of dynamism within when you're actually looking at either training your model or running inference in various aspects of things. All right, so from again another basic set of this one is from TensorFlow standpoint. Session is by default where where almost the entire TensorFlow runtime is essentially defined within this particular session object itself. So or if you define a particular graph, let's say the earlier graph that we defined where you had two adds and a single null. If you would want to, let's say execute this particular graph, you need to define a session. So it kind of creates a, let's say, uh, place where you can actually execute this particular model with different inputs and probably get different outputs as you go along. So this is config proto is a very interesting aspect of it. So TensorFlow, when you the runtime itself actually supports variety of configurations. There is a concept of what is called as intra-op parallelism and inter-op parallelism. Remember, I talked about data flow architectures being very friendly to parallel computing. So there are it actually supports variety of options, and you can actually there are default values to it, but you can change these default values in the config proto object file. So in this case, interop parallelism essentially defines the number of graph operations that I can execute in parallel, right? So here you're saying minimum 2 graph operations that I can execute in parallel. So in this case, I could, if the TensorFlow runtime can detect that, hey, I can run my add operation and my mul operation in parallel, it'll actually go ahead and do that. Right, interop parallelism, INTRA op parallelism is essentially defines how much of parallelism that I can actually achieve within a single node itself. Right, so can I create number of, let's say for example I'm doing a simple matrix multiply. Right, can I create maybe n number of threads to accelerate matrix multiplication at the end of the day. Right, so there is a very clear differentiation between interop and intra-op. Right, so this is probably the reason I'll come specifically come to this reason why this becomes very important when you would want to extract performance on the CPU standpoint, right? And all you essentially need to do is there is a default object that you can extract from tf.config proto. You can make all the optimizations that you would want to do, and then you can pass it on to tf session, and bingo, the session object takes in the configuration protocol, reconfigures the TensorFlow runtime to take advantage of whatever default parameters that you have mentioned. Well, okay, so I have, a place where you can actually store data, but feed underscore dict is the way by which you can actually feed data into it. So we'll look at how to feed data. So in this particular case, we are essentially passing a dictionary, which we say that, hey, for my input A, my value is 3, and for input B, my value is 2. So in this particular case, I'm creating a dictionary of values, and I'm passing it to my session, and it'll automatically assign let's say the input 1 placeholder to have the value of 3, and the input 2 placeholder to have the value of 2, and go to the next step, which is essentially my computing my add operation and my mul operation to get the final output in this particular case, right? So so the session, okay, in this case, the session.run is something that is by default that is required for running evaluating any sort of operations or your TensorFlow variables. So you would need to invoke a session.run for let's say for in this case I want to get the value of t, and I essentially pass this feed underscore dict. Remember, feed underscore dict is the dictionary value that I passed earlier. So in this particular case, to obtain the value of d, then I need to get the value of c, which essentially depends on a and b, right? So it essentially executes this entire graph, and it in the end gives you the output variable, which is the value of d. Okay, so in the end, if you take a look at it, you define a computational graph, which is a static model. Well, you can with the fold, it becomes a dynamic model. But then you would run your graph with taking advantage of session or a session run placeholders and all those things like that to essentially either train your model and then run prediction on top of it. Okay, so I have. Is queues better than? Yes, yes, queues are better than feed underscore dict. Now there is a very nice TensorFlow article that has been written on the TensorFlow page. I think it's a performance guide that's available. Feed underscore dict was the first when TensorFlow came out, they essentially used feed underscore dict, but since then they have come up with different ways by which in data which and is more performance friendly. So I would essentially take a look at this performance guide that's available on the TensorFlow page. It gives you good PKMs in terms of how to how to feed in data into your TensorFlow model at the time. Uh, how is okay? So the question is, how is Intel using TensorFlow? What are their use cases? Well, I would the answer can be answered in two ways. One is as a deep learning framework. So we are accelerating the framework so it can run better on our hardware. Now, whether we are using it internally for our own purposes, I'm not sure for our purposes, but I'm sure that there are multiple groups in Intel who are essentially using TensorFlow. But we are working with the with the industry, with the academia for taking advantage of variety of use cases that we are essentially seeing in the market that that people are looking at or people seriously want to implement it going forward. The would be is ai.intel.com. There is a blog page, or there is I think there's also a case study page for the solution cases. I think there's a link out there, a whole bunch of articles that we have worked on with the industry and things like that. And yes, I think there's also I think we do have a team that does very active research for variety of use cases. I think one that we recently launched was something as a kind of an open source project called as NLP Architect. This talks about acceleration for standard NLP algorithms. I think you may want to take a look. It's not built on TensorFlow, by the way, but it's some kind of a research project that we have done. I think reinforcement coach, I think, is another library that we have recently launched as well. So ai.intel.com has good material for all of that. I would, I think you would, please go through that. And I think you should be able to get a good idea in terms of the use cases. What percentage like training, 70%, testing 30%, can we run 80-20? Well, that's actually a very difficult question. So the idea of separating training and validation is the fact that you don't you have two separate data sets that you are training on, and then for validation as well. So it really depends upon your choice at the end of the day. But idea is you give majority of it for training because you have a large enough data set that is good enough to achieve higher accuracy, because there has been good research that has that many people have proven that the more the data that you have, you can get good enough of accuracy as long as your your model is good enough. But you can get higher and higher accuracy if you have large enough data set as well, right? But but split your data in a fashion that you give a majority of the training, but you do keep a separate validation set by which you will be able to measure how accurately your your model is being trained. So just separate it out. But the aspect of whether you want 80-20 or 70-30 is kind of is up to you at the end of the day. Can you, any practical example for TensorFlow, can you explain and brief? Okay, okay, let's I think let's see if I can pull something out. So there, okay, so there is a recent I think a paper that came out with how we used TensorFlow with our specifically on the inference standpoint for for medical imaging. So we I think this was for let me see if I can pull that paper out. Just give me a second. Let's see this. I think ai.intel.com. I think it should be available on that particular page. I'll probably guide you to that if my page opens up. And yeah, so here you can actually take a look at it. You can actually go to library white papers. You can look at this one white paper called Tabula. Tabula is a software as a service solution provider, which looks at providing 360 recommendations for multiple publisher sites. So they essentially used, I think, if I'm not wrong, if I understand correctly, I think they used TensorFlow for recommendation based engine. Yeah, I think this is on TensorFlow. Yes, they use TensorFlow, and this is probably one use case that we can that we can really talk about. I think the other one was Yeah, I think you can look at this medical imaging on Intel CPU-based systems. So this is with Philips, where we essentially looked at patient X-rays and computational topography CT scans to essentially see how we can accelerate deep learning frameworks. So there are good white papers out there. I think you can please take a look at it. I think there are and also if you would want the GitHub, if I'm not wrong, I think they have a separate GitHub link for models. It's got a great wide variety of fully functional TensorFlow models. Including for object detection, for image classification, and I think for recommendation engines. I think there's a whole bunch of stuff that you can essentially take a look at it. Okay, do I need a GPU machine to run on TensorFlow, or will it run on a 16 GB RAM Windows server? Well, yeah, let me answer this, right? So if you are depends on what you are looking at to do at the end of the day. If you are if your model or your let's say computational task is good enough to run on a 16 GB machine. Remember, most of the deep learning models really require a really extremely large data set. So 16 GB of RAM in many cases is really not that large enough. So you would be probably, whether you use a GPU system or you would use a Windows server, you're going to be more limited by memory than anything else. So I would look at trying to see if your use case that you're planning to implement really fits well within a 16 GB environment to first start around with, and then probably explore how you can get better performance out of the road, right? But my suspicion is you would be probably more limited by memory than anything else, right? So let's probably okay, GitLab links that you were talking about, where are they listed? So you're talking about, I'm assuming that you're talking about the Swan TensorFlow models. I think, let's see, I'm not able to type in the answer here. Okay. I'm not sure about the GitHub link, but please look for, I think, TensorFlow models on GitHub. I'm sorry, I think this is what I can remember right now, but you can definitely search for TensorFlow models on GitHub, and you should be able to get access to that, right? I think we answered this and this. All right. Okay, let's probably go. I think we are kind of running out of time. Okay, neural network models. Okay, so this neural network model essentially looks at it uses your brain neurons as an inspiration. It's not exactly a replica of it, but uses as inspiration. Neural networks essentially started off from an extremely probably around the 70s, where they were called as ANNs. It's called as artificial neural networks, and the goal was to see how they can build on previous neurons in this particular case. So if I have a layer, then can I essentially build on the output of that layer so that I can do more complex tasks and so on and so forth. So as I'm essentially taking advantage of output of one layer and feeding it as input in another layer, can I essentially run more complex tasks, complex tasks, and see if I can possibly get some sort of output at the end of the day. So this is kind of inspired on this particular on your how your brain has been defined, designed. It kind of follows on how TensorFlow is. I'm not going to talk about it because I think I've spoken in much detail. But in this particular standpoint, if you it kind of the way it works is it remember I talked about the edges. Let's say, for example, the edge into this particular two edges into the add compute node. You have two of them. One that's coming out as an output of matpl, and the other that's essentially p, right? Now I can kind of assign some sort of not exact. P is actually a bad indicator in this case. Let's say, for example, I replace b with another computational node. Let's say, for example, add. Right now, I can assign some sort of weightage to these particular edges. Let's say, for example, I can assign more heavier weight to the output that is coming from my matmul to add versus the one that's coming from my second add, right? So in that way, you essentially compute the above function, which is essentially it's essentially W transpose X plus B, where X is defined as the inputs, and W is essentially the weights that is assigned to each one of those edges, and B is the bias, right? So you essentially the entire single neuron essentially talk about is executing function, and then you essentially so what you're essentially trying to do is you're multiplying the weights with the inputs and trying to figure out if by you're looking at trying to see what is the exact weight that I need to assign to this particular edge so that I can predict a specific output, right? And this bias essentially helps you control the overall neuron function itself. We'll talk about activation in the next slide, but activation kind of, okay, actually it's gone to the next slide. Okay, activation kind of, applies to, brings in a non-linearity to it. So non-linearity is if you take a look at MATML or any sort of addition operations, these are all, even convolution and things, these are all linear activation functions. So, they essentially go from, one stage to another, but they're pretty much linear in nature. But if you would want to, do some, let's say, if you really would want the model to, to really, help you predict something, or if you really want the model to help you identify something, then the nonlinear activations that, play a significant role in this particular standpoint. So because it brings in some sort of a nonlinearity into the entire equation, thereby, giving you the ability to, help you, define your model in a fashion that it'll actually be, let's say, for example, if you want to predict a cat or a dog, in this particular case, the activation functions does play a very significant option for you. Okay, this is again taking away the visual noise. I'll probably skip this particular aspect, and this is kind of reworking the exact same aspect that I talked about. You have different nodes that are edges that are assigned to the sigmoid variable, and you can essentially assign weights to it. You can pass inputs to it. You essentially do a computation, mathematical computation between the inputs and the weights, and thereby allowing. So depending upon the weights, in this case, you can get different behavior. So if you pass in different inputs, you'll with different weights, you can essentially activate probably the sigmoid function on the top or the sigmoid function on the bottom, depending upon how, depending upon the weights and the inputs that you have given. So, so in this way, you are able to bring in some sort of, you are able to, direct the deep learning model to essentially figure out, the exact output at the end of the day that you're looking for. Okay, I'll probably look at, looking at convolutional neural networks. Yeah, so this is the basic premise. So I'm not sure how many of you have played around with computer vision. So computer vision essentially tries to see if can I infer things from images in this particular case, right? So can I detect edges? Can I probably detect a straight line? Can I detect a curve? Can I detect a face? Right, so that's what computer vision typically looks at. So it's trying to interpret data from images and videos and things like that. So they essentially, look at, so they would essentially depend upon feature vectors, right? So they would essentially define a small kernel that will define, let's say, for this case, on the right hand side, if you take a look at it, I have a 4x4 kernel, which essentially has, given. If you take a look at the red ones that are out there, which essentially tell, okay, these are the ones that I'm interested in. 1 is the ones that I'm interested in. 0 are the ones that I'm not interested in, and things like that. So I can essentially define my filter, depending upon the kind of operation that I want. There are very well defined filters for edges, curves, and straight lines and things like that. So what convolution neural net essentially does is it takes these filters and applies it to the image, and the activation that you get, the output that you get, is essentially areas in the image that that the particular filter word could detect. Let's say, for example, if the filter is about detecting lines, and I pass an image of, let's say, of a building, then the output is essentially about and like it could be another image, but in all cases it could be it's called as an activation map, which essentially has let's say non-zero values for specifically those areas where the filter essentially detected edges. And then you can pass this output map to another, let's say, for example, another filter where you're looking, let's say, for example, maybe um, let's say a window. Then you can essentially feed in a filter for that particular purpose, and then the output map of that would essentially be a place where it was able to detect this particular window, right? So the convolutional neural net essentially works on in stages, so where you essentially pass filters, and you are able to get an output map, and then you're able to further operate on additional layers and take it and go on and go forth. So the goal at the end of the day is so that you essentially get a sort of a distribution, and you can look at using this particular distribution. You can probably using a fully connected layer, you can in the end detect whether whether you're looking at the probability of the specific object is whether is helping you detect whether it's probably or if it's a cat, or if it's a face, or if it's a dog, and things like that. So if your fully connected layer helps you in this particular detection. Isn't Intel coming up with its own GPU? Well, we have our own GPU. We have so it's called as Intel Integrated Graphics. It's been available for many years. It's been predominantly available on the desktops and the laptops. So many of the Core i3, Core i5, I think a few of the Core i7 platforms already has Intel integrated graphics. Well, there's a lot again beyond that. Yeah, there's a lot of activity that always happens in Intel. As we look at get more information about it, then we'll definitely talk about that. Can we say CV led
Mukesh,
to
sorry to interrupt you, Mukesh.
Yeah, sorry. Yeah.
Actually, we are already behind time. So, will it be feasible
Okay.
that we take the QAs after the session?
Sure. No problem. No issues. I'll probably good point. Let me Swan, thank you for highlighting that. So this is what we essentially talked about. Convolution can be essentially implemented by one call within TensorFlow. It's called as convolution 2D. Here you pass the input parameter, which is essentially a 4D tensor. Remember, I talked about it's essentially a multi-dimensional array. Think of it in that particular fashion. But multi-dimensional arrays have different flavors in different programming languages. But the very simple analogy would be that here is the filter that you would probably apply. So this is the you're providing the kind of the filter that you would want at the end of the day. Strides and padding essentially defines this is where you play around, right? And you look at should I probably skip a row? Should I probably skip a column? I can essentially play around that, and these are all depending upon what is it that you're doing at the end of the day. So from a programmability standpoint, TensorFlow convolution does give you the ability for strides and padding for you to achieve what is it that you would want to do at the end of the day, right? And for again, I talked about training and inference. Remember. I also use this concept as a trained concept of model being trained. So the idea behind deep learning is very simple. The aspect is the fact that you actually have a data set and you have the corresponding output values as well, right? So think of it this way that let's say for example, if I have a whole bunch of images, then I have I essentially want to detect let's say emotions in this particular data set, emotions on people's faces. So I do have what is typically known as the ground truth data as well, so which essentially tells that okay, this particular label means this is where it's a smiling emotion, or if it's an angry emotion, or if it's a maybe let's say a sad emotion and things like that. So I essentially have a I have a label data set which essentially tells that hey, for all the outputs that I have the ground truth that I have I already give for this particular let's say for training, right? So now what deep learning essentially does in this particular standpoint, or any model that does for whatever, let's say for example, I'm detecting emotions in this place. So I have an input data which could be a whole bunch of images. So it essentially goes through this whole deep learning network. It goes through various layers. It goes through various activation symbols. And at the end of the day, what it essentially does is, it goes through this particular output, right? Now, the output is essentially compared to the ground truth, right? You essentially want to compare the fact that, hey, did this particular model in the end predict, let's say I'm looking at a smiling face. So did the deep learning model predict a smiling face? Like how close am I to the truth, right? If it, let's say, for example, let's say it did not do anything, it actually it detected sad, right? That means to say that, the model that you essentially trained was for detecting smiling faces, but it actually helped detect a non-smiling face, right? So that means to say that you have to train the model, right? Now you essentially go back to, you essentially start feeding, back to the network. So essentially called as back propagation. So essentially correct, a whole bunch of things. In this particular case, when you talk about correction, you're essentially talking about correcting the weights, because the weights essentially define what, what are those input, nodes that or rather the nodes within each layer that I need to activate. So you essentially do a whole bunch of back propagation. Back propagation is essentially doing the same computation that you were doing when you went to the forward pass. You essentially do it in the backward pass. So let's say, for example, on my left hand side is the input, and on the right hand side is the output. So when I essentially do training, then I would do one forward pass. So essentially go from input to output. In the output, I essentially would do a comparison to the ground truth to see how far am I from predicting the correct output. So then, then I would feed the entire data back, back to the, through the output. So I would essentially go from output back to the, the hidden layer that is essentially connected to output, so on and so forth. So I do everything in reverse. So until I come back to input again. So now in each of these stages, I essentially modify the, to get a different set of weights. Then I go through this process again, applying it for a whole bunch of, images. So I kind of do this iteratively over multiple, time steps, or as typically known as epochs, right? And the goal at the end of the day is, to see how, how my model is converging. So when I talk about converging, is how, is my model converging towards closer to the ground truth, or is it diverging away from the ground truth itself? So if let's say, for example, if my model that is being trained is sufficiently enough that every time I do, go through the training run, my error rate drops, right? That means I am actually, every time, let's say, for example, I started off from 90% error rate, then as my iteration goes, I drop to 60, 40. And that means to say that my model is slowly converging. That means every time I get the output, my probability of actually detecting a smiling face increases, right? So now this is an iterative process. This essentially goes, and depends upon how big your model is, how many epochs that you're planning to run, or how many training steps that you have. At the end of the day, it could run for, typically on days and weeks and things like that. So training is pretty much an extremely computational intensive job, because you're essentially doing the same task twice, one in the forward pass and one in the backward pass as well, right? So it does take, and again, now that's just one iteration, right? And you're doing this over, all the images, and you're doing it again and again and again until you're able to converge to a good probability of, let's say, in this case, a good smiling face at the end of the day, right? So after you are as a a developer of the model, you essentially say that, hey, this is something that I have trained. You essentially take this trained model, and now you essentially deploy it in in real time, right? So let's say, for example, you would want to probably deploy it, and let's say, for example, in some place, probably in probably for entertainment in some place where you want to detect smiling faces and probably print out emojis for whatever purpose at the end of the day, right? So you would essentially take the train model, and then you would deploy it, and this is essentially called as inference, right? I think there was a question that came up earlier whether training is faster or inference, but remember, inference is just essentially one forward pass, right? There is no backward pass at all. There's no back propagation as you do in the training step, right? So inference essentially ends up being less computational intensive than training, and thereby you are able to, and also it's considered pretty much lightweight version of training itself at the end of the day. So you would be able to get good performance from that from that particular standpoint. So I'm sure if that answers your question, but if not, please ping on the Q&A, then we'll definitely do that. Right. So I'll quickly.
So,
Yeah. Sorry.
Mukesh, before we start, there
Yeah.
is another poll coming up that and a question that I would
Okay.
ask to the audience.
Okay, so I gave a very quick overview of TensorFlow. I am sure there's a lot of other features that TensorFlow folks keep releasing out. I really would suggest going to the TensorFlow documentation and also the models for you to really get a quick, really good idea in terms of what all capabilities that the framework supports in general. Let me talk right now about what we have done from an Intel standpoint for optimizing TensorFlow. As I said, all the optimizations that that the teams have been working on have been added to the master branch of TensorFlow. So you should be able to get all the latest greatest optimizations from the master and all the other releases as well. So as I said, the releases, I think right now the stable release is 1.10, and I think 1.1 RC2 is currently out there. So you should be able to take a whole bunch of get a whole bunch of accelerations as well. So so again, if you want to take a look at it, you can look at ai.intel.com/TensorFlow. This is where you can get all the curated material for TensorFlow from Intel. This is one kind of a one-stop landing page for you to take a look at. Right. So let's see. Okay. So there are ways by which you can do that. So there's this. I want please note down this link. It's called as you can just go to software.intel.com, Intel Optimized TensorFlow Installation Guide. This is this is a very good guide that essentially tells you where you can get the latest TensorFlow binaries or the wheels in this particular standpoint, or you can essentially get you can use pip install. You can use Anaconda wheels are possibly another way by which you can get access to the latest we take advantage of certain libraries, and by enabling those options when we build TensorFlow, it gives us that ability to accelerate that. You can get what are the options that we enable through the TensorFlow performance guide. I think there is a link that essentially points you to extracting performance of on the CPU. It tells you even how to build for taking advantage for the CPU and right. So this talks about 1.6. It's a pretty dated one. There is the 1.10 is already available out there, so you can take a look at. So just do a pip install. 1.10 TensorFlow, and you should be able to get whichever Python version that you're looking at the end of the day. All right. So I know there is there are releases that we constantly do. You can take a look at this particular page for you to get quick access, or even the ai.intel.com/TensorFlow will give you links to where you can download the latest wheels for the CPUs. Right. Okay. Intel. So what we have predominantly done is we have kind of looked at three basic accelerations. Pretty much one on the when we talk about operators. Remember, we talked about operators are essentially the computational primitives that TensorFlow looks at. We looked at graph-based optimizations. We'll look at what is it that we have done in that space, and probably and also system-level optimizations as well. Remember, I talked about config proto. We will talk about how we can take advantage of the config proto as well to get better performance on the CPU, right? The operator optimizations is very simple. If you take a look at it, remember this is going back to the same earlier graph. If everything is a data flow diagram, you do a matml add, and you essentially do a relu activation. Is there a way by which we can probably accelerate this particular aspect? Right. So TensorFlow, when it came out, was it essentially leveraged a library called as Eigen, mainly for the CPU standpoint. So what we essentially did was replace this with highly optimized kernels. through in a library called as MKL-DNN, right? So you can take a look at MKL-DNN. This is a open source library from Intel, which essentially provides you computational primitives for deep neural networks, right? So it's got a whole bunch of very actively supported page, rather project. We constantly are adding more and more computational primitives. So most of the accelerations that many of the frameworks take for running on the CPU are essentially driven through the MKL-DNN for computational primitives, right? So this is one aspect that we did. So we essentially replaced all the the eigen calls that were being made for, let's say, for example, for convolution 2D or for max pooling or ReLUs and things like that, or batch normalization and things like that. So we essentially replaced it with alternatives which are more efficiently tuned to take advantage of the underlying CPU architectures, right? So this is kind of a quick snapshot. If your people are aware of ResNet 50, ResNet 50 is one of the popular frameworks that is used for image classification. And on the on the right hand side, what you essentially see is the default one. It is running on the CPU, and this essentially uses all your not exactly unoptimized, but these are essentially still C calls, but they don't take advantage of the underlying architecture. So you take a look at the wall time that essentially, let's say, fused patch norm gradient would take. It takes around probably around 8 seconds. Whereas in this particular case, we essentially replaced it with let's say MKL fused patch norm, which is the more optimized version for the x86 architecture, which takes around 184 milliseconds, right? So this is the performance difference that you are essentially taking, getting by taking advantage of optimized libraries like MKL-DNN at the end of the day, right? And a whole bunch of optimizations. You talked about backprop and convolution 2D and things like that. So right, so that's one aspect of it. And the other thing that we essentially did was with specifically with graph optimizations was let's can we essentially merge nodes, right? So let's say, for example, in this case is you have a convolution 2D and then you have a bias. So like, can I essentially do a convolution 2D with bias? So rather than have two nodes, can I essentially make it into a more probably one node which is probably more computationally efficient? Thereby I will be able to take advantage of, by merging these two nodes, I can essentially introduce a whole bunch of software accelerations to take advantage of the architecture itself. So this is one of the aspects of it. We essentially worked with multiple topologies. We kind of identified a couple of nodes that can essentially be merged. We essentially created either primitives for them, or we essentially work directly on the TensorFlow runtime itself to essentially optimize them at the end of the day. This is another example where we essentially did, in the earlier case, you essentially had an input bias going into the ReLU function. But in this case, you really don't have the convolution essentially going into ReLU. So, we could essentially merge both of them so that we'll be able to make it, a little bit more efficient from a computation standpoint, right? The other aspect, which we look, remember when we talked about deep learning essentially uses a lot of large data. So so memory copying essentially becomes a significant overhead, right? So you don't want to have the data in multiple formats. So which essentially means to say that you have to copy the data from one format to another format, which is it's kind of unnecessary computational cycles are being wasted because of this particular aspect. So and also the other aspect that we looked at was maybe the unoptimized layout was probably very expensive, because I'll talk about that a little bit in a couple of slides later. But certain the CPU architectures like the data to come in a certain format, right? So can we take advantage of that? So the whole aspect of trying to create an optimized layout was to figure out how can we convert into an operation which will probably make it more let's say friendly for the CPU, and that's what these layout propagation essentially talks about. The all the so the kind of operators that MKL-DNN essentially uses, they use all optimized memory layouts, right? So the MKL-DNN in general essentially uses all these optimized layouts, which is fine-tuned for the CPU at the end of the day. All right. If you take a look at this particular aspect, I think in the earlier graph, if you take a look at it, there's a bunch of redundant operations that we do. We do multiple converts, right? So this is kind of this is something that we can avoid. So rather than what we essentially do is, when we essentially get the input, can we have it converted into a specific format that we want? We apply an MKL in this particular case it could be a convolution 2D based on MKL-DNN, directly feed it to MKL relu, or in the earlier case we essentially could do even with fusion as well. So we could essentially do MKL convolution with relu, and then finally reconvert it into a format that probably that can be understandable for TensorFlow or any other future operations down the road. So thereby we essentially, by not only having it saved in an optimized layout and getting rid of redundant operations, we are saving a lot of expensive memory copies. Thereby you will be able to thereby save computational cycles and thereby accelerating the overall performance of the application at the end of the day. Right. At another level, what we look at was system optimization. So remember, we talked about interop-parallelism, interparallelism, and things like that. Interop and intra-op are essentially that variables that are defined by the TensorFlow runtime. OMP num threads is a variable that is defined by MKL-DNN, right? So typically we keep the OMP num threads equivalent to intra-op parallelism number of threads. So because I remember we talked about intra-op parallelism is essentially the number of if I take a single graphical node, can I essentially parallelize that graphical node as much as I can? So if I essentially have a computational job, and if I want to take advantage of MKL-DNN to do it, then I would essentially MKL-DNN is essentially threaded using a runtime called as OpenMP. It's a standard for parallel programming. By providing OMP num threads equal to number of interop, then you're essentially saying that, hey, let's say for example in this case you're creating interop of 8 threads, then I can do I am setting setting OMP num threads to 8, so that if I'm doing a convolution 2D with 8 threads, then MKL automatically creates 8 threads in parallel so that you can execute this particular job, right? So we essentially use this particular these 3 variables. There are a whole bunch of other variables as well. So additional variables that we expose called something called as KMP affinity and KMP block time. These are very well documented on the ai.intel.com/TensorFlow. You can essentially take a look at that. I think there are enough examples that will essentially tell you, how you can configure this to take, if you can play around with these settings. These are all runtime settings. You don't have to play around with the model. You don't have to, let's say, for example, you don't have to worry about layer fusion because it's already done by the TensorFlow runtime. You don't have to worry about, taking advantage of MKL-DNN because the TensorFlow runtime has already been built, so that if anytime it encounters, let's say for example, convolution 2D, rather than calling out, the default one, it essentially accelerates itself through MKL, convolution 2D. So most of the aspects is, it's already been built or baked into the the Intel optimized TensorFlow. But these are runtime configurations that you can essentially play around to see, hey, does this value make sense, or does this value, maybe interrupt? I have it 1, 2, 4, depending upon what kind of model that you have, or how much data set or the workload that you have. You can essentially play around with it to see, can I execute more workers in parallel, more operators in parallel to see if I can get better performance. Remember, I talked about this particular, class, Python object called as config proto. Config proto essentially has a whole bunch of options. You can both for, I think for CPUs and GPUs as well. But from a CPU standpoint, the ones that at least we are interested in is these 2 variables. So by just setting these variables, you can, you can get any, TensorFlow session, runtime to, take advantage. Get the TensorFlow runtime to be configured so that it can every time it encounters a TensorFlow graph, it knows the fact that it has the ability to run 2 graph nodes in parallel, and each graph node can create a maximum of 56 number of threads, right? So it can do that. More details can essentially be found in this particular web page. As I said, there's an excellent page that you should look for. It's a performance guide that has been released by the TensorFlow authors, so it's should be able to get a lot of details about how to accelerate performance. Well, yes. So you do end up a little bit of so incorrect settings will make will cause poor performance. It may also end up causing some sort of failure. So you would have to play around with these settings. That's the reason I said, depending upon your model, depending upon the CPU or the platform that you're running on, you may want to fine tune it for the environment. There are some default settings that we have seen for certain standard topologies. I think they are already available on the public website. You can take a look at it. I think I'll also share some guidelines here for some of the popular topologies, and then you can essentially do that. But in case you encounter some of these errors, like OMP system unable to allocate errors, then the hint would be to kind of reduce the OMP number of threads, which means probably you may also have to reduce the intra of parallelism threads as well. So you can actually kind of infer from that particular standpoint. So here we go in our performance guide. This is what we give. We give for popular block time. So we essentially set KMP block time equal to 1. So this is the way, if you are very familiar with Python, then you can essentially use the OS Python module to set these particular variables so that it is globally available for the particular Python session, and then probably take advantage of that as well. So you can look at this particular TensorFlow guide for more additional details. The format that we essentially look at is NCHW. So this is a 4D tensor, which essentially talks about I think number of samples, the channels, height and width. Data format, I think we're already. I think in the next set of slides we also show the fact that we are also working on taking advantage of if the data format comes in a different way, like an NHWC, which is number of samples, height, width, and then the channels, right? So even if it comes in that specific format, we do we take advantage of both these formats, because both of them are very popular. NHWC is something that the GPUs use because it's more friendly for them. For us, NCHW is also there, but we have accelerated both NCHW and NHWC for it. So depending upon, you don't have to worry about what format my data is, as long as it adheres to any other format, you should be able to get performance on the CPUs. Again, it's kind of reiterating the same data, but this is the web page. You can take a look at it. There is a very nice article that essentially talks about how do you optimize for the CPU. And you should be able to, this is constantly updated, or you can essentially come to the visit the air.intel.com website for additional details as well. So this is a kind of ballpark figure that you would get using floating point 32. We essentially looked at 14x of throughput performance by comparing it against with the default TensorFlow, which was essentially based on Eigen. This is with ResNet 50, and this is the inference output where we were able to just achieve around 3.2. This is actually pretty dated. You should be. I think there are additional performance that has already come into play, and as we get more details, we'll definitely share it on the public website as well. But we essentially use this particular recommended benchmark suite that TensorFlow, that from TensorFlow and Fox itself. So we essentially use that for replicating these numbers, and it's actually part of the I think there's very nice white paper that has been written on how to achieve these performance as well. So if you want to try it out on this specific platform on the right hand side, then you should be able to get close enough performance as well. This is the kind of performance that we had. This is the kind of X percentage, kind of X performance that we got around both to multiple formats. So 8x to compare to the default backend, to all the way to 14x as well. So depending upon whether it's NCHW or NHCW, we are getting close enough parity in terms of performance as well. So we really don't care which format it comes in. I think we should be able to give you performance on both these vectors as well. right? So so inference is something that we will definitely look at. So from a computation standpoint, yes, training definitely has an edge over inference. So we were able to get much better performance because we were able to accelerate a whole bunch of training performance as well, right? So in summary, this is sorry, it's a very quick overview about what how Intel has optimized on TensorFlow. Again, a quick overview on what TensorFlow is and how you can essentially use neural networks with TensorFlow. As I keep saying, the updates that are available, you should be able to go for ai.intel.com/TensorFlow. So I think that's probably an excellent page. You should highly recommend. There's also a newsletter that's available. If folks are interested to get in newsletters in your email, I think I would please sign up for that. Or you can bookmark your this particular web page, and I think you'll definitely come across some interesting articles that keep getting published on the blogs and white papers and things like that, right? Um, so TensorFlow has two levels of acceleration. Firstly with framework MKL-DNN, secondly with MKL enablement. MKL set equal to true. With MKL, without MKL, does it fall back to eigen or default blast? Any public acceleration? So, okay, so what we have done is, MKL, so the way we started off was, most of the deep neural network primitives, first appeared in MKL. Um, we started using MKL deep neural networks that initially, but that became an open source project, so it essentially became MKL-DNN. But we would still take leverage the SGEM. So typically your a single generation matrix multiply or single precision matrix multiply is something is a core of your convolutional neural networks. That was essentially we used to leverage with taking advantage of the MKL library. So, but recent releases of MKL-DNN, we have released an open source variant as well. Pretty much most of the operations that we do are essentially through MKL-DNN as well. Now, if you do not build with MKL, sure, I think the fallback would be eigen. I think it would fall back to eigen as well. But the performance numbers would pretty much be with MKL-DNN as well. So the performance that I just shared was all with with MKL and MKL-DNN. Do you meet the? I think you mean the math behind it or IT infra wise. So if you can be a little bit more specific, then probably I can give you a better answer. But I think this is from Swapnil. If you can possibly phrase your question a little bit in more detail, then maybe then I can give you a better answer. Performance numbers with MKL-DNN, and so this is essentially, I think let me go back to this particular slide. All these numbers that you are seeing on the screen right now are with MKL-DNN. So when you talk about eigen, which is the default, which you think of it like MKL-DNN plus MKL turn to false, and the performance that you see is 8.6x, or for VGG16 is essentially the gain that you are getting with MKL-DNN set to be true. Can TensorFlow be used for more accurate time series? I think it can be. I think there are good number of white papers that I see where deep learning, generally in deep learning frameworks being used for time series kind of workloads. I think yes. I think some of them have been written on TensorFlow. I think there are a couple of models that are already available. I think you should be able to get some access to some very good papers for that particular standpoint.
Okay, so Mukesh, sorry to interrupt you again. So can we
Yeah,
go with the polls now?
yeah. Please do, please do. I think
Yeah.
I've answered all the questions, but yeah, if there are more, then we can.
So before we wrap up, audience, we have a couple of questions for you. So please answer them. So for example, the question is, are you aware of TensorFlow optimization for the Intel Xeon scalable processors? Okay. So I repeat. So like, are you aware about the TensorFlow optimizations for Intel Xeon scalable processors? So right now we can see that around 80% of the people have said no, and they were not aware about this TensorFlow optimization.
So one aspect of when we talked about Xeon scalable platform, the numbers that you essentially see, remember what you see on the right hand side is the model name. Is essentially Intel R Xeon registered Platinum 8180. So this is essentially the Xeon scalable family. So Xeon the Platinum 8180 CPU is the Xeon family as well. So the numbers that you're essentially seeing is being generated on the Xeon scalable platform. So since you were not aware of it, so and I did not specifically tell you that these are scalable platform. Yes, so now you know that these are scalable platforms. So maybe Kunal, if you can repost the question, then maybe we'll see if people get multiple. If if you can actually flip the value itself.
Yeah, I'm pretty sure about it. Okay, so if you don't mind, then we can proceed ahead to our
Yeah,
third
sure.
question in that case.
Yeah, please.
Okay, just yeah. So this is about whether have you heard about the Intel AI Dev Cloud? Okay, so before this, if you have ever heard about the Intel AI Dev Cloud, please vote yes. Otherwise, no. So here I can see that this is the same distribution as for the previous question. Around 87% of the people have not heard about the Intel AI Dev Cloud. Mukesh, maybe you can try and comment on something this.
Okay, so Intel AI Dev Cloud is is kind of a let's say I can't call it as it's kind of an environment. I think of it like okay, for a want of a better word, I'll probably call it as a, developer cloud, where you can probably get access to the latest TensorFlow environments. You can actually sign up; it's for free. I think you get access to the the Xeon scalable platform that we just spoke about. I think you can you get access to this particular environment. You can run it. You can um, uh, you can run your TensorFlow environments, you can run your models, and I think you get some amount. I think you get a, I think you get, I think it's for a time period of a month or so, where you can get to play around with, all the optimized TensorFlow environments. You can run your models on top of it, and things like that. So if you want to get access to the latest scalable platforms, and you want to run deep learning models on top of it, you can definitely do that. There is a if there are this is basically from, and you just want to give it a try, right? You just want to try to see what's happening. You just want to play around with it, or if you want to learn and things like that, you can definitely take advantage of that. But the other case, let's say for example, if you're a serious user and you really like to you really want to evaluate it from a production standpoint, or you want to deploy you want to evaluate from a deployment standpoint, then there is I think there is it also links to a program that we have called as AI Builders. So you can definitely take a look at it. It's called as aibuilders.intel.com. So it's a very specific program for software companies who are using deep learning and things like that. So that they also get to use the AI Dev Cloud as well for specific purpose. So there's a very specific program as well. So I would suggest you can just go through probably Google or Bing or whatever is your favorite engine, and just search for AI Dev Cloud, and you should be able to get access to that. And similarly for AI builders as well.
Okay, that's great, Mukesh. If you want to possibly answer some more QAs, or for example, if you want to say something else, you can please proceed ahead.
I think there is one question that essentially talks. I think they talk about. I think it's probably so all the optimizations that we talk about are essentially under MKL. So whether we take advantage of MKL-DNN or MKL, it's all under this umbrella called MKL, right? So the config opt that you essentially would pass when you are building with this one, then it will be all under MKL as well. So think of it as default path, one with MKL, which will allow access to accelerated primitives, computational primitives for that can that allow you to take advantage of the CPU, or by default a fallback to an eigen implementation. So these are the only two paths that you would get for TensorFlow, from at least from a TensorFlow optimization standpoint. Can this Intel optimized framework work for Intel CPUs or can work on AMD Ryzen? I don't know. I have not evaluated on AMD Ryzen, so I'm really not sure about it. I know I don't want to give you a wrong answer, but I really do not know, right? I think that's probably what I can give because I really have not evaluated on Ryzen platform to give you honest feedback. All right. So what are some challenges that you're facing? You see implementing TensorFlow for first timers. Well, TensorFlow in general is it really depends on which part of TensorFlow that you would want to play around and what is the use case that you're looking at, right? So if you're looking at from implementing a low level API, then TensorFlow can be a little bit of it can take has a little bit of a learning curve, right? So that is one aspect of it. So but they're trying to make it very simple. So you have a high level APIs like Keras or estimator API. So you can take a look at it from that particular standpoint. So you can definitely learn at that. So you really don't have to understand the underlying low level details about TensorFlow, at least low level API calls that we just spoke about, like tf.session, config proto, and or session.run or placeholders and things like that. Well, it's not exactly placeholder, but you still have to define. But at least the sessions and things like that, you don't have to worry about it. So it is something that would automatically be taken care of by either your Keras or things like that. But I think the difference in Keras is you can create there are preset models that TensorFlow comes up with, so you can definitely use that. Or Keras, you still have to create models, but it's a very high level that it's many people find it easy to essentially use Keras as well, right? But beyond that, the next aspect is essentially your workload of choice. So what is it that you're trying to do? Whether is it from image processing standpoint, then if it's image processing, then there are very popular topologies that are actually available out there. A lot of quite a like ResNet 50 or VGG16 and things like that are very popular. You can take advantage of it. Or if you're doing, let's say, like for example, object detection, then mobile net SSD and things like that. So there are or YOLO and things like that. There are very popular frameworks, topologies that have already been quite used by many people. So they do have multiple implementations of it. Probably you can take use of it and then probably fine tune it for the data set that you're looking at. Same thing for NLP, same thing for machine translation and things like that. There are a good set of models that are available. Quite maybe the ones that are probably in the cutting edge of research. Many of them have been released. Let's say, for example, NMP and transformers and things like that. And all you would need to do is fine tune it for the use case. But if there are probably for specific use cases that are that may not be readily available, then you may have to build something out on your own. And there are good excellent articles. The Stack Overflow is a very you can actually submit your questions on Stack Overflow. I think you have a lot of people answering questions there. Very active support that you can definitely get from people. Even on the Intel side, there is a AI forum that you can definitely post your questions as well. Experts will definitely come in and answer your questions as well. So you can definitely take advantage of multiple forums to do that.
Okay.
Okay, I
Yeah.
think
Okay.
these
Okay.
are
So
the few
before,
questions that I had.
yeah.
And
Okay. So before we wrap up this night with your final words, I just have a last set of couple of questions that I would ask the audience to poll for, and then probably we can have a final words from your side, and then we can wrap up the night.
yeah, sure.
Sure. So here are a set of last questions, people. Okay. So here it goes. So the first one is please rate your feedback on the content presented. Okay. So how do you think this webinar was? And what did you learn? Rate accordingly. There are multiple of options: excellent, good, very good, neutral, poor. Please don't shy from giving critical feedbacks. Okay. And the second question is, what topics are you looking for in the next webinar, whether it's artificial intelligence, machine learning, deep learning, IoT, or HPC? So these results will help us to better the webinars and cater to the needs, your needs basically. So just a couple of more seconds and then I'm going to end the poll and share the results. Okay. So probably Mukesh, then we can have final words from your side for the night for the audience, and then we can probably wrap up.
Okay. I think uh, well, yes. So one probably one final thing that I would leave behind is there are a lot of work that is being done by in making sure that let's say by multiple people across the world, across academics, industry, and things like that, to solve deep learning challenges. So it's a very active field, very interesting field. People who are interested in this field, I think should spend more time if possible. Um, and please do keep visiting the ai.intel.com website. You will definitely get a lot more access to a lot of material. And please feel free to raise questions on the forums. And if you don't have, if you need answers, and people will be there to help you out at the end of the day. All right, and looking for a good set of interactions as we go along.
So I was saying, Ki, thank you so much for your words. It was really nice to have you here. Uh, it's a pleasure that we'll have something to ponder over tonight in our heads. And I thank you once again for being with us. I also thank our audience for joining us. So if you have any sort of questions, please use the discussion forum Stack Overflow, as Mukesh said. And feel free to check out our trainings portal blog section for the exciting new content that we have. And also do not forget to check out Data Hack Summit 2018 that is coming up in November. Please do check and have a good night. Thank you for being with us.
Okay. Thanks, guys. Thanks, Kunal. See you guys later.
Thanks, Mukesh.